Continuing on with our discussion on probability is about marginal probability, conditional probability, and related probability concepts. So let's look at this scenario. First, suppose all 100 employees of a company were asked whether they are in favor of or against paying high salaries to the CEOs of the US companies. So we have a table in the next slides. We have two classifications for these responses among 100 employees. So the each employee would respond either in favor or against. So here is the table that we have. So male and female employees voted either in favor or against. So we have here a total of 60 male employees and 40 female employees, and voting in favor and against, a total of 19 in favor and 81 against. So a total of 100 respondents in this sample. So we have here a marginal probability. So because we want to explain this concept. So marginal probability is the probability of a single event without consideration of any other event. So how will we relate marginal probability in our example? So here, the marginal probability, for example, here is just one event. So we basically have two events here. So either you have you are in favor or against. That's one. That's basically two basic events, and then you have here either you're a male or a female. Two outcomes of uh, another event. So basically here, a marginal probability is, say, what's the probability of having a male respondents? That's just 60 out of a total of 100 respondents. So that's 0.60 or 60%. And that's one marginal probability. And another probability is what's the probability of being a female respondent. So that's 40 over 100 or 0.40. So basically here you can see that regardless whether you vote in favor or against, you are just considered either you're a male or female. So you're just considering one of the two possible outcomes of a certain event. So that's your marginal probability. So you don't whether you're male or female, regardless of, for example, here, the votes in favor. There are 19 votes in favor. Sorry, there are 19 votes in favor out of 100 total respondents. So regardless whether it's a male or a female who voted, so it's still counted as the probability of those in favor. This is the marginal probability, regardless of any other conditions. Okay, now we have here conditional probability. Conditional probability is the probability that an event will occur given that another has already occurred. So we have event A. If A and B are two events, then the conditional probability of A given B is written as P, A, and then you have your vertical slash here, and then B. So this is read as the probability of A given that P has already occurred. So here you can see, it's a bit, people get confused here because event B by this time should already have occurred, even though it comes after. In writing this probability, B comes after. When you write it, B comes after A. But in the conditional probability, what this notation means is that the event A happening given that this event that comes after in writing has already occurred. So let's have a look. So here is our another notation for that. It's the probability. So let's look from the previous example. What's the probability of voting in favor given that that voter or that respondent is a male? So being a male or female has already this event has already occurred. And how many are those in favor among those that are male respondents? So basically that's your probability. So we can read this one. The probability of those in favor given that the respondents is male. So let's look at this example. So what's the conditional probability of P in favor given it's a male from a data of 100 employees given previously? So we look at those only male respondents and how many in favor over, of course, now the probability here is different because instead of the denominator being 100, which is the total number of respondents, it's the total number of male, those that are in event B or in that is specific, the specified outcome in event B. So basically, the event B here is the male or female, so it's a male. So the total number of males is 60, so that's your denominator. And those in favor is 15. So 15 over 60 over, which is equal to 0.25. So do not confuse it, the denominator here. So the denominator here should not be 100, which is the total number of respondents, but rather the number of male employees. Okay, number of male employees here. So let's have another example. What's the conditional probability that a randomly selected employee is a female, given that this employee is in favor of paying high salaries to CA? So this one is a female. So this is a different way to actually express it. So this is a bit different here. So previously, how many what's the probability of the respondent being in favor given that the respondents are male? Now here, in this another example, what is the probability of getting a female respondent among those that are in favor of paying high salaries? Now, the order of events becomes different. So here you will have here the precondition, or the condition that comes first must be that you have high those in favor. Because look here, the condition here in the previous example, what's the probability of getting a respondent that is in favor among the male respondent? So the condition that comes first here is a male respondent, and you are computing how many are those in favor among the male respondents. In the second example, you are looking first at the respondents that are in favor, and what is the probability of getting a female respondents among those in favor. So it's a switch around. So look at the calculations now. So first, we need to consider how many are those in favor. So we have a total of 19 employees in favor, and among them, there are 4 females. So the calculation now becomes the number of females in favor, which is 4, and over the total number of employees who are in favor, which is 19. So take note that the difference in the notation. So previously, it's in favor given that the respondent is male. Now, the probability is now a female given that the respondent is in favor. See the difference? So the condition of whether you're in favor or not, or rather the respondents, or the condition that you must be in favor, comes first before considering whether you're a male or a female. So basically, this is your that's the issue with this conditional probability. You need to know which comes first, because in the calculation, the one here, the condition that comes first becomes your denominator, or rather the condition that is written last. Okay, so it's a bit confusing about that. So the condition, the precondition, or the condition that comes first, is usually written in this notation last. Okay, so the denominator here is 19, which is the condition, the precondition, the condition that comes first before this condition of being a female, which is also in favor. So here the calculation is 4 over 19 over which is equal to 0.2105. So in conditional probability, it's very important to know the order of the events, which condition comes first. Okay, so we now have mutually exclusive events. So what are mutually exclusive events? Mutually exclusive events, events that cannot occur together at all. So they are impossible to occur at the same time. For example, you cannot be for instance, let's look at the grading system in Mapua. You cannot be a runner-up for Dean's List given if you have a grade of 5. So that means you're already disqualified. So being a Dean's Lister at the same time having a grade of 5 in your transcript cannot occur at the same time. So they are mutually exclusive events. So let's consider this example. So consider the following 2 events of a randomly selected adult. Y is this adult has shopped on the internet at least once, and N, this adult has never shopped on the internet. So the events Y and N are they mutually exclusive? So can this, is it possible for this event to occur at the same time? Is it possible that a certain adult has shopped on the internet at least once but has never shopped on the internet at all? So these are basically mutually exclusive events. They cannot occur. A person cannot both not shop, never shopped at an internet store, and at the same time a shop at least once at an internet store. So either you have shopped or not. So these are mutually exclusive events because they cannot occur at the same time. So we now have a different term which is independent. So two events are said to be independent if the occurrence of one does not affect the probability of the occurrence of the other. So mutually exclusive and independent events are different in such that exclusive events cannot occur on the same person at the same time. But independent events, they are two possible events that can occur at this person at the same time, but it doesn't affect whether it happens to you or not, given that the previous another event has already happened. So there is no effect. They do not have any connection with these events. Have no connection to each other, but they can occur at the same time. They can also occur, not occur at the same time. Regardless, they really have no effect on what each other whatsoever. So you have here the probability of A. Basically here, in terms of notation, we can say that events A and B are independent events given that the probability of A occurring when B has already occurred is equal to the probability of A occurring, and the probability of B occurring when A has already occurred is equal to the probability of B occurring regardless whether or not A has occurred. So this is basically what it means. P of A is a marginal probability notation because it just looks at the probability of A occurring regardless of anything else. So whether the probability, this condition that probability A has occurred given that B has already occurred, is the same as the probability of A occurring regardless whether A or B has occurred. So basically that's that's the definition of independent events, A and B. So let's have an example. So in a survey, 500 randomly selected adults who drink coffee were asked whether they usually drink coffee with or without sugar. So of these 500 adults, 240 are men, 175 drink coffee without sugar. Of the 240 men, 84 drink coffee without sugar. So you have here two events, drinking coffee without sugar and being a man. So are they independent? So basically, you need to look at, well, of course, we would say that, well, regardless whether or not you're a man, you could drink coffee with or without sugar. It's a choice of personal preference. But that's a subjective answer. So we need to look at probabilities. So we have here the definition of independent probability must be that the probability of A occurring given that B has already occurred must be equal to the marginal probability of A occurring. So here we can have here drinking sugar and a man. So the probability of drinking coffee without sugar, that is, you have how many respondents? 175 respondents out of 500 adults. So this is the probability of your drinking coffee. So this is 0.35. So 175 divided by 500 is 0.35. And the probability of drinking coffee without sugar, provided that you are a man, is how many first? The previous event, the precondition is being a man. So how many men in the respondents? So we have 240 men. So let's look back. So 500 adults, 175 drink coffee without sugar. And then 240 of them are men. So 240 men, 84 drink coffee without sugar. So here, the probability of drinking coffee without sugar, provided that the respondent is a man. So you look just at the male respondents, and how many of them drink coffee without sugar. So that's the denominator is 240 and 84 drink coffee without sugar. That is both a man and a coffee drinker without sugar. So that's 84. So this is 0.35. So since both probabilities are equal, so these two events, drinking coffee, you drink coffee without sugar and you're a man, are can be considered independent events. They have no relation to each other. So whether you're a man or a woman, you can drink coffee without sugar, or whether if you're a man, you can drink coffee with or without sugar. There's not no harm in that. Okay, so that's basically knowing whether a certain probability is mutually is independent or not. So here is the gender, drinking coffee with or without sugars. Okay, so let's look at complements. Complement of event A, which is denoted by A bar. So with a bar or A complement is an event, we define a complement as an event that includes all outcomes for an event that are not included in A. So if you have, for example, a drink coffee without sugar, but you can also drink coffee, okay, for example, you want to drink coffee, well, how do you like your coffee anyway? Black coffee without sugar, black coffee with sugar, coffee with sugar and milk. So those are possible events. So let's say that the event A is drinking black coffee without sugar. Therefore, the complement is basically the events that are not included in the outcomes that are not included in the event, which is drinking black coffee without sugar. So what are those outcomes? A black coffee with sugar and a coffee with sugar and milk. So those two events are the A bar or the complement of the event A, which is drinking coffee without sugar, or rather a black coffee without sugar. So basically that's your complement. Call the others. So for example, here is your event A, and all other possible outcomes in your sample space is the A bar. So here, let's look at another example. So in a group of 2,000 taxpayers, 400 have been audited by the IRS at least once. If one taxpayer is randomly selected from this group, what are the two complementary events for this experiment and what are their probabilities? So here we define A, which is the taxpayer that has been audited by the IRS at least once, and the rest of the possible outcomes, which has been A bar, selected taxpayer never been audited by the IRS. So we do not have 2,000 taxpayers, 400 have been audited at least once. So here, of course, the probability of the A, which is audited by the IRS at least once, 400, over the total number of taxpayers is sort of 0.2. Now, how do we calculate the A complement? The A complement is basically calculated by just getting how many, because it's the number of the A complement responds to the all other outcomes aside from A, means 400, rather 2,000. How many respondents do you have? Subtract the 400 respondents that are included in A, and that is the A complement, which is 16,000. So 2,000 minus 400. So that's your 16,000, and that's your marginal probability of the A complement. So 16,000 divided 2,000. Or you can just get 1 minus 0.20. You get 0.80. Because it's the all other probabilities aside from A. So that's your probability. It's actually refers back to the second property of probability, which is the sum total of all outcomes of a certain experiment must be equal to 1, which this must be equal to 1 because the A complement is defined as the all other outcomes aside from A. Okay, so let's look at intersections. So in intersection, so let A and B be two events defined in a sample space. The intersection of A and B represents that the collection of all outcomes that are common to both A and B. So if you remember your set in math, the set of numbers, intersection of two sets, basically these are elements that are that have the outcome of A and B, both getting A and B. So let's have, here is the notation of that. So you have two sets A and B, and the intersection of that, the overlapping region, is the intersection where the respondents on that region must have both A and B, experience A and B, or falls under outcomes A and B. So in the multiplication rule, so the probability of the intersection of two events is called a joint probability. So how probable is getting inside? So for example, you have two events A and B. What's the probability of getting both A and B event at the same time? So calculating your probability of getting inside that shaded region is the multiplication rules. So the probability of getting the intersection of two events is their joint probability. That means the probability of getting event A and B at the same time. So to calculate that is if A and B are two independent, take note that they must be independent events. If A and B are independent events, you just simply multiply the probability of getting A and multiply the probability of getting B. Okay, so let's have this example. An office building has two fire detectors. The probability that is 0.02 that any fire detector of this type will fail to go off during a fire. Find the probability that both of these fire detectors will fail to go off in case of a fire. Assume that the other of these two fire detectors are independent of each other. So you have two fire detectors. Each of them has a probability of being defective 0.02% of 0.02 probability. That means 2% of the time. So what is the probability that both will be defective? So the probability of A, let A the first fire detector failing to go off, and B the second detector failing to go off. So the joint probability, since they are independent events, A failing to go off has nothing to do at all with B failing to go off, and vice versa. So they are independent events. So the probability that both are defective during a fire at the same time are probability of A times probability of B. And this is just multiply 0.02 times 0.02, which is 0.004. So you have a probability of 0.04% of both of them failing at the same time, which is very, very small. Okay, let's look at another example. The probability that a college graduate will find a full-time job within 3 months after graduation from college is 0.27. So 3 college students who will be graduating soon are randomly selected. What is the probability that all 3 of them will find full-time jobs within 3 months after graduation from college? So let's say A, B, and C. So we denote them as the student A, student B, and C. So the condition here, or we want to calculate that all 3 of them must be able to find full-time jobs within 3 months. And the probability of a certain person getting a full-time job is 0.27. So, meaning, probability of A getting a full-time job is 0.27. Probability of B getting a full-time job is 0.27. Probability of C getting a full-time job within the time frame is also 0.27. So, multiply each other and you will get the probability of both A, B, and C, all of them getting the full-time job within 3 months is 0.0197. Pretty low, huh? Okay, so let's look at the multiplication rule for joint probabilities of 2. How about we have been doing independent events. What if the events are dependent? So the probability of the intersection of two dependent events A and B. So what if A and B are basically, when we say dependent, is that one event occurs provided rather the effect of, for example, A and B. The probability of A occurring is also affected by the probability of the event B occurring. So we have here probability of both A and B occurring is equal to the marginal probability of A, which is basically a probability of A occurring without any condition to B, and probability of B occurring provided that A has already occurred, meaning B is dependent on A, or it can be vice versa, probability of B occurring and the probability of A occurring given that B has already occurred. So let's look at an example. So this is the classification of all employees of a company given by gender and college degrees. So you have male and female, and you have basically male and female, and college or not college graduate or not college graduate. So these are our table. So if one of these employees is selected at random for membership in an employee management committee, what's the probability that this employee is female and a college graduate? So what's the probability of getting a female and a college graduate here? So if you're going to calculate the probability of the intersection of the events female and college student, so the probability of getting a female is 13, because if you look at our table, the event is being a female. So regardless whether you're a college graduate or not, it is a female. But the second condition is you must be a college graduate. So the probability the college graduate, the probability of getting a college graduate among the female selected employees is 4, because that's the number of female college graduate employees. So that's the number, and the total among this, the precondition is being a female. So we have 13 female female from the selections. So 4 over 13. So this is the conditional probability. So what's the probability of being a female and a college graduate? So just multiply both probabilities. So the probability of getting a female and the probability of being a college graduate, given that you're a female, is, so 13 over 40 times 4 over 13, this is 0.10%. So that's the probability of getting in your in this event. This is the probability of being getting a female and a college graduate among the females. Okay, so basically when you look at the intersection, being a female, both a female and a college graduate, there are only 4 within this intersection region. So if A and B are 2 events, then for the conditional probability, so if the A and B are 2 events, then the probability of A, rather the probability of B occurring given that A has already occurred, is equal to the probability of A and B occurring over the marginal probability of A. And the probability of A occurring given that B has already occurred is the probability of A, the joint probability of A and B over the probability of B. So this is actually another way to look at it. Basically, this is just the conditional probability a while ago, and we just switch it around. So if the probability of A is not equal to 0 and B is not equal to 0, of course, because they're denominators. So let's look at this example. The probability that a randomly selected student from a college is a senior is 0.20, and the joint probability that a student is a computer science major and a senior is 0.03. So what's the conditional probability that a student selected at random is a computer science major given that the student is a senior? So the probability of being a senior is 0.20. That's let's say P of A, that's a marginal probability. And the probability of getting a science major, computer science major, given that you are a senior is 0.03. So we can you have this one 0.20, and the intersection, which is being a senior and a computer science major as well, is 0.03. So what the probability of getting a computer science major who is also a senior is 0.3 divide 0.20, that's 0.15%. So that's the probability of getting a computer science major given among the seniors. So it's a much higher than the intersection, because here among all of the students, it's both a senior and a computer science major among all of the students. That's why it's smaller. So if you're just going to narrow down our scope and look among the seniors, what's the probability of getting a computer science major among the seniors? Remember, in this calculation, the senior is the denominator, the number of seniors. So you have 0.03 divided 0.20. So the probability is a little bit higher because the denominator is smaller, rather than this one, because this is an intersection where you are a senior, both a senior and a computer science major among all of the other students. So this is a higher probability because you're just going to look at seniors and what's the probability of getting a computer science major here. Okay, so joint probability of mutually exclusive events. The joint probability of 2 mutually exclusive events is always 0 because 2 events cannot occur at the same time. Therefore, there is no intersection among them. So, how about union? Let A and B be 2 events defined in a sample space. So, the union of events A and B is the collection of all outcomes that belong to either A or B or both A and B. So, here you have A or B. All 440 employees of a company were asked what hot drink they like the most. So the responses are listed in the next slide. So what's the union of events of being a female and likes regular coffee? So here is coffee or tea. So males and females. So here is we have a total of 440 respondents. So there's also other. So neither coffee or tea. So we have here a total of 440 respondents. Among them, 150 are females, 290 are males. So we have 150 female employees and 170 uh, respondents who like regular coffee. And we have a female that likes regular coffee is 60. So we are looking at uh, females, respondents who are female or likes regular coffee. So we just add 150 plus the number of females is 150 plus 170, which is the number of respondents, whether male or female, that likes coffee. However, we subtract 60 because this is the intersection, which basically the 60 is already counted in the total here and it's already counted in here as well. So we have an excess of 60. So 150 plus 170 minus 60, which is the intersection. Because otherwise, you will count the females who like regular coffee twice. They will have a double counts instead of just one count. So you have a total of 260. That's the union of events where if you are a female or you like regular coffee. Now that's the difference between intersection. An intersection is that both events must be the same. For example, if it's a female and likes regular coffee, so the answer must be 60 because the respondent is a female and likes regular coffee. That's 60. But what is being asked is a female or likes regular coffee, is that you need to get the union, so get the total of number of people who likes regular coffee. And since it's a female or there are also female who doesn't like regular coffee, so you need to get a total number of females, and then you just subtract the intersection because otherwise they will be counted twice. Okay, so you have here, this is your union of events. So unlike intersection, which is also only in this region, for union of events, as long as they are within the events that are outlined here. So we have here addition rules. So mutually non-exclusive events, the addition rule is to find the probability of the union of two mutually non-exclusive events. Now here, unlike the multiplication rules are for events for the end, both the intersections of the event, whereas if it's just a union of the events, you apply addition. So basically, here's the difference between and the or. And is the joint probability, which is which denotes intersection. Both conditions must be met. That's why you multiply. And in addition rule, it's just whether either or both conditions, and so you just it's a union, so you would just simply add. So the portability of the union of two mutually non-exclusive events is A and B. So whether A or B, the probability of getting A or B is equal to the marginal probability of A occurring plus the marginal probability of B occurring minus the intersection, the joint probability of A and B occurring at the same time. We have to minus this one because the intersection, otherwise you will count the intersection twice. So you will have a higher number than what is really the actual number because you count the intersection twice. So, for example here, the university president has proposed that all students must take a course in ethics as a requirement for graduation. 300 faculty members and students from this university were asked about their opinion on this issue. So we have a table in the next slide, which is a two-way classification of the responses of these faculty members and students. So what's the probability that one person selected at random from this 300 person is a faculty member or is in favor of this proposal? So take note here, the keyword here is or. If it's and, it's a joint probability. If it's or, it's just a simple additional or union of two possible probabilities. So you have the or. So favor and oppose, whether you're a faculty or a student. So favor, oppose, or neutral. So total is 300 respondents. So we are looking here is, let's me go back. So what's the probability of one person selected at random from this 300% is a faculty member or is in favor? Faculty member or in favor. So let's look at the number of faculty members. We have a total of 70 faculty members and those in favor is 135. Now, the event where a person is both in favor and a faculty member is 45. So this is our probability. So 70 over 300, that's 0.233. So that's a marginal probability of being a faculty member. And the marginal probability of being in favor is 0.45. And the probability of the intersection of both, basically being a faculty member and also in favor among all the respondents is 0.15. So we need to count what is the probability of being among the respondents, you're a faculty member or you are in favor. So you get 2.33 plus 0.45, this marginal probability is less this intersection, the joint probability. So this is 0.533. So that's the probability of getting a person at random, and then it's either in favor or a faculty member. So how about union of mutually exclusive events? So the probability of two mutually exclusive events is just simply add the two probabilities together without needing to subtract the joint probability of both. The reason is because since they are mutually exclusive events, the joint probability is 0. So there is no possibility that both A and B are occurring at the same time on the same person. So you just add the marginal probability of both events. So let's say, what's the experiment of rolling a die? What's the probability that a number less than 3 or a number greater than 4 is obtained? So the probability of getting a number less than 3 is, what are those numbers? 1 or 2. And what's the probability of getting a number greater than 4? So what are those numbers 5 and 6? So what's the probability of getting 1 or 2? Or 5 or 6? So getting a number that is both less than 3 and greater than 4 is impossible in rolling a dice because there is no number less than 3 but greater than 4. So here, for example, the probability of the event less than 3, we have two events here, getting a 1 or a 2 among 6 possibilities. 1, 2, 3, 4, 5, 6, of course. And this is for 6-sided die anyway. And the probability of getting a number greater than 4, what are those numbers? 5 and 6. So getting 5 and 6 among all the 6 possible outcomes is 2 over 6. So just simply add them. It's equal to 4 over 6 or 0.667. So this is the probability of getting a number less than 3 or greater than 4. Okay, let's look at counting rules, factorials, combinations, and permutations. So counting rule to find total outcome. So if an experiment consists of 3 steps, and if the first step can result in m outcomes, the second step in n outcomes, and the third step in k outcomes. So if here you have an experiment, 3 steps occurring, each step has a different number of outcomes. So how many possible outcomes that you have? So in this experiment, you just multiply each other. So total outcomes is about 4 outcomes, m times n times k. So that's basically the total number of outcomes. So for example, 3 tosses of a coin. How many total outcomes of your experiment? Go back to our decision tree. You have 2. Each event has 2 outcomes. 2 times 2 times 2 is equal to 8. So those are the total number of outcomes. So when you there are if you toss a coin 10 times, so that's 2 raised to 10. Okay? Okay, let's have another example. A prospective car buyer can choose between a fixed and a variable interest rate and can also choose a payment period of 36 months, 48 months, and 60 months. So how many total outcomes are possible here? So what are the choices? First, you can choose between fixed and variable interest rate. And then second step is the payment period of 36, 48, or 60 months. So we have the first outcome has 2 and the other has 3. So 2 times 3, which is 6. So these are the number of possible outcomes you have. So let's have another example. So you have the National Football League will play 16 games during a regular season. Each game can result in one of 3 outcomes, whether you win, you lose, or a tie. So how many total outcomes? So among 16, so 3 outcomes for each 16 games. So 3 raised to 16, which is equal to 43,046,721 outcomes for all 16 wins. Now, let's look at factorials. So, it actually used to count the outcomes initially. So, we have, I think you have seen this symbol n factorial or n exclamation point. That reads as n factorial. It presents the number of all integers from n until 1. So, for example, n factorial is n times n minus 1 times n minus 2 until you get to 1. So, also another definition is a 0 factorial is always equal to 1. Okay, let's look at 7 factorial. 7 factorial is equal to 7 times 7 minus 1 is 6. So 6, 7 minus 2 is 5. So when count down until you get to 1. So 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1. So that's your 7 factorial. For 10 factorial, again, count starting from 10, count down, multiply each digit counting down from 10. So that's your answer. So how about 12 minus 4? Parenthesis factorial. Of course, with all other rules in mathematics, it's the PEMDAS rule. Do the activity or do the operation inside the parenthesis first. So 12 minus 4 is 8, and that is your factorial. So count down from 8 until 1. So 5 minus 5 is 0 factorial, and by definition, 0 factorial is always equal to 1. So how about combinations? Combinations is the number of ways x elements can be selected from n elements. The notation used to denote the number of combinations is your n elements, and the combination of x occurring given n elements. So basically, that's how you read this combination. So basically, you read as the number of combinations of n elements selected x at a time. So n denotes the total number of elements, which it comes first, and x denotes the number of elements selected per selection. So the number of combinations for selecting x from n distinct elements is given. So how do you calculate this value? So the combination of x occurring given n elements, you have n factorial, the total number of the elements n, over the event x factorial times n minus x factorial. Actually, there's in your calculator, you can just directly input ncx there. So you have n factorial x factorial over n factorial over x factorial times n minus x factorial. So let's hear an example. So an ice cream parlor has 6 flavors of ice cream. So you want to buy 2 flavors of ice cream. So if you randomly select 2 flavors out of 6, how many combinations of flavors or ice cream with flavors do you have? So we have here combinations. So when we say combination, so out of 6 possible flavors, we just choose 2. Okay? So when we say combination, so it's either say strawberry and chocolate and strawberry, they are the same combination, is counted as 1. So here we have a total number of 6 ice cream flavors, and you have number of ice cream to be selected is 2. You just select 2 out of the 6. So how many possible combination of flavors you have? So apply the formula 6 factorial, which is the total number of events or flavors that you have, and you can just choose 2 among them. So 2 factorial times 6 minus 2, which is 4. 4 factorial, you get 15. So there are 15 ways for 15 different combination of flavors. So 2 ice cream flavors out of the 6 available flavors you have. So let's have another one. So 3 members of a committee will be randomly selected from 5 people. How many different combinations are possible? How many possible groupings that you might have? So you have n is 5 people, and you just select 3 out of the 5. So how many possible groupings, that combinations of people that you have? So you get 10. So just plug in the equation. Okay, so another example, Marvin Sons are advertised to hire a financial analyst. The company received application from 10 candidates who seem to be equally qualified. The company manager has decided to call only 3 of these candidates for an interview. If she randomly selects 3 candidates from 10, how many total selections are possible? So you just apply the possible combinations of choosing 3 out of the 10. It's 120. Okay, let's look at the next example, which is permutation. So how is permutations different for combination? So we have a permutation notation similar to how you do combinations. So permutations give the total selection of X element from N elements in such a way that the order of the selection is important. So the permutation notation is similar to the combination, but the difference between permutation and combination is that in a combination, as long as the two elements are grouped together is fine regardless of the order. But the permutation must be that they must be of the same order. So the order here matters. The order where each element was selected from the n elements. So the number of permutation of selecting x elements from n elements is arrangements because we have arrangement here matters. So the following formula is used to get the permutations. So the denominator is smaller here because there are much more possible arrangement given if you just have, for example, selecting the ice creams. You have you getting a chocolate and strawberry. That's just one combination of a chocolate and strawberry flavor. But choosing whether the chocolate comes first over the strawberry or the strawberry comes first over the chocolate is are two different permutations. Although in combination they are the same. You both have chocolate and strawberry, but if the chocolate is put first in the scoop of strawberry comes first over the scoop of chocolate, that means you're gonna eat the chocolate first anyway. So that's a different call between the chocolate coming first and then the strawberry on top of the chocolate where you're going to eat the strawberry first. So that's entirely different in terms of arrangement. So that's a difference between permutations and combinations. So let's have this example. So a club has 20 members. They are to select 3 office holders, president, secretary, and treasurer for the next year. They always select these office holders by drawing 3 names randomly from the names of all members. So the first person selected becomes the president, the second is the secretary, the third one takes over as treasurer. Thus, the order in which the 3 names are selected from the 20 names is important. So for example, A, B, and C. So let's say Maria, Sam, and Karen are those 3 names. So if we look at the combination, it's just Maria, Sam, and Karen being picked, all 3 of them is just one event or one possible outcomes of all other possible outcomes. It's just one outcome of all other possible outcomes. But it becomes a different scenario if whether Maria becomes the president, Sam becomes the secretary, and Karen becomes the treasurer, or Karen becomes the president, Sam is the secretary, and Maria is the treasurer, or what other comment? Sam is the president, Maria is the secretary, and Karen is the treasurer, or Sam is the president, Karen is the secretary, Maria is the secretary, Karen is the sorry, Maria is the treasurer, Karen is the secretary. So arrangement is important because there will be different scenarios even if the elements are just the same. Okay, so for under 20 total members and 3 are to be selected but in order, so there are 6840 possible permutation. Actually, the same can be applied with our genetic code. So we have 4 possible letters or nucleotides. We have 4 nucleotides and the codon has 3 nucleotides per codon. So how many possible permutations? Because again, the order numbers, even if you get UGA and UUU, those are different. One is a subcodon, the other is an amino acid codon. So the order matters. That's a bad example. So for example, UGG and GUG. So both of them has 2 Gs and 1 U nucleotide. So getting a UGG, GUG, GGU, each of them denotes to a different amino acid. So that's a permutation already. Okay, so that's it for probabilities and permutations.